So actually, we kind of ended last time. Basically done. We talked about this notion of equipotential surfaces. Those are kind of important, and the notions that you can build off of them are useful. But that's all we're really going to say about them. They'll show up occasionally, so keep that in mind. If you do want more information on them, go look at the Libre text. There is more detail there than I provided, and it'll hopefully shore up your understandings. So today we're going to begin with something that we really should have done last time. We didn't really have time to do, though, unfortunately. And we're just kind of going to fly through it. We're going to skip some stuff. It's important, but I do want to get some more material. This is this business of energy diagrams. So energy diagrams are the last subsection in, I think it's chapter 4. I don't remember. It might be like section 3.7 or something like that. I don't remember off the top of my head. Yeah, it's section 3.7. So let's talk about energy diagrams. So far, we've talked about this notion of potential energies, and we've given formulas for the potential energies for gravity and for the elastic force, but we haven't really given any good ways to visualize these things. And so energy diagrams are basically just a visualization of how a system's energy evolves or how a system's energy changes depending on the configuration of the system. Now, when I say configuration, what I really mean is where are the objects? How does that affect the energy of the system? So what an energy diagram is it's a graph of the potential energy function in terms of position in space. So like, horizontal position, for example, as well as graphing the total energy of the system. So the reason why we have to do this is because if we just graph the potential energy function, then that wouldn't be specific to any one system, because the potential energy function for the potential energy function for a rock that's 10 miles up is the same as the potential energy function for a rock that's thrown sideways, right? So we need to add more information that specifies the system. In particular, we need to add information about the total energy of the system. And by the way, all of this business that we're going to do here is assuming there are no non-conservative forces. If there are, then this whole business of energy diagrams kind of goes by the wayside, because it doesn't make sense. It doesn't really make sense to talk about energy as a function of position then. No, there wouldn't be a graph for thermal energy, because thermal energy doesn't depend on position. It depends on the path that's taken to get there. So there's a lot to extract from these types of diagrams. So let's look at a simple case just to get going. So this is just an object under the influence of gravity, and only that. So we know that the potential energy function for an object under the influence of gravity, U sub g, as a function of y, so the potential energy varies with vertical height, y. This is just mgy. Now we could add a constant. All that would do would be shift up all the total energy of that would just shift up all of our graphs. So we choose to make that constant 0. It doesn't actually matter though. So then our plot looks something like this. I'm going to do my best to draw this. So we have y over here, where this is height. So this is the height of the objects that we're considering. And let's say that our system, whatever system that we're considering, just has some amount of energy. Let's call that total energy E tot. So when I say graphing the total energy, what I really mean is this. And so this is to say that regardless of where the object is, because there's only non-conservative forces and there's no external forces, because there's only conservative forces and there's no external forces, the total energy is conserved, right? This is the statement that 0 equals delta KE plus delta PE. It just means that this is the change in the total energy is 0. So that's why the graph for the total energy is constant regardless of where the object is. So we would plot the total energy. Typically, it's done as a dotted line, horizontal dotted line at the level of the total energy. By the way, this vertical axis, this is energy. So this would be like 8 joules or 1,000 joules or whatever. Then we plot our potential energy function. So our potential energy function in this case is just a line that starts off at the origin and has slope mg. So I'm just going to draw something. Let's draw it like this. There we go. That's terrible. I'm sorry. There we go. That's as good as it's going to get. Sorry. So we could, but I'm not really worried about that right now. Like I only showed this amount of the axis just because it's the only part that's relevant here. But you know what? Just for, okay, how's that? So now we have information about several things. We know that what the potential energy is at a given place, because the potential energy at a height y is given by this function, right? So we now know how much potential energy there is at a given place, and the total energy is just the sum, is just the sum of the potential energy and the, it's the sum of the potential energy and the kinetic energy. So what we can say then, what we can establish, is that this amount here, this would be the potential energy, however much it has, that height, and this amount, let me use a different color, this amount, this is the kinetic energy, because the total energy is just the sum of the two. And so what we can see is we can see that as the potential as potential energy increases, the kinetic energy decreases, and so on. Now there's an extra step, there's an extra feature here that I haven't pointed out yet, and that's there's a special point right here. That point is when the potential energy equals the total energy. And so it turns out that at that place, the kinetic energy has to be 0. And in fact, if you wanted to try to go beyond that place, say over here, the kinetic energy would have to be negative. Kinetic energy typically goes from the potential energy to the total energy. And so if it goes up, it's positive. If it goes down, it's negative. So here, from the potential energy to the total energy would be negative. And you can't have negative kinetic energy because kinetic energy is just 1/2 mv squared. It's always positive. So this region to the right of this point where the potential energy equals the kinetic energy or equals the total energy, that is called the forbidden region. Or more particularly, it's called the classically forbidden region. But don't worry about that. So this is to say, at this point, which we call maybe y max, this is the maximum height that the object can have. Does Ke represent the no, Ke is the kinetic energy. This maximum height is a turnaround point, i.e., if you were imagining an object just being thrown upwards, it will travel upwards and upwards and upwards, its kinetic energy decreasing as it moves to the right, and its potential energy increasing as it moves to the right, until it gets to a place where the kinetic energy is 0 and the potential energy is equal to the total energy. At that point, it can't go higher. It doesn't have any more speed. So at that point, it will turn around and fall, and hence turnaround point at that height, and hence the kinetic energy will increase again, and the potential energy will decrease again. So these places where the total energy is less than the potential energy, those are forbidden regions, meaning that objects that have that total energy can never be at those locations. So think of this as, this is a set of y values that the object that we're describing is just not allowed to be. It just physically cannot be there, because this would require kinetic energy less than 0, which is not allowed. Because kinetic energy by definition is positive. So let's look at another example. Did you say potential energy would fall and Ke would increase when it falls? Yeah. From at its maximum height, its potential energy is at a maximum. Then it falls, its speed is increasing, so its kinetic energy is increasing. So let's look at a more complicated case. Let's say that we have a spring attached to a wall at x equals 0, and it's horizontal. So the picture is something like you have a spring, and then you have a mass attached to it. Maybe it has an equilibrium place. When the spring is stretched this much, it's at equilibrium. If we want to get there, we must increase. Yeah, exactly. Call this x equals 0, and then we'll call this position here x. It's just its coordinate, right? So let's plot the potential energy for we want to plot the energy diagram for this situation, but we need to first know what the potential energy function is. Now we know that the potential energy function for a spring, the convention is that we set the constant to 0. So in that case, we set the constant to 0 so that the potential energy is 0 at equilibrium. So then our potential energy function in this coordinate system is just 1/2 K times x minus x naught all squared. Okay, Now let's plot our potential, our potential energy. So by the way, in this case, it doesn't make sense for our block to go to the left of x equals 0. So we're not going to plot the position left of x equals 0. It just doesn't make sense because it would have to pass through the wall. So here, let's do this plot again. And I'm actually going to zoom it in a little bit. There we go. So let's say that this place is x equals x naught. And let's say that we have, and again, like the amount of total energy that you might have might be given to you, or you might have to solve for it or whatever. But let's say that the total energy is just here. And we know that that's the total energy just because, you know, maybe we know how far the spring was pulled. So initially when it was released, maybe it was stretched a certain amount and then it had 0 speed. So we can calculate the total energy by knowing what the total energy is initially. Oh, I don't need x equals x0 there. And so in this case, this just looks like a parabola centered at x equals x naught. So here we have the x coordinate. Here we have energy again. And so our energy diagram would look something like this. That's a really good parabola. I'm going to give myself some credit for that. So here we have 2 turnaround points, here and here. So we might have x max is what we might call it. That is the maximum possible x value. And so basically think of it this way. The spring will pull back harder and harder until it makes the speed of the block 0, and then it'll turn around. And the same thing will happen here. The spring will push back because it's being compressed harder and harder until it makes the block turn around. So you have x min here, x max there. These are both turnarounds or turnaround points because they are where the object turns around. They are the place where the kinetic energy vanishes and all of the energy is potential energy. So that means that these regions, let me make this better. These regions are forbidden. No, it shouldn't. So just like before, if we want to find the total, if we want to find the kinetic energy, all we do is we evaluate the potential energy at a place. Say here, that's the potential energy when it's stretched that much, when the block's coordinate is that value of x, and then the kinetic energy is this much. And so you can see that actually the kinetic energy in the middle is greatest. When it is at equilibrium, the kinetic energy is maximum and the potential energy is at a minimum. Now, there's a little bit of a subtlety here, not a subtlety, but an interesting feature. And that's at this place, at x equals 0, we have an equilibrium point. At x equals x naught. So can I show x min? I thought the block couldn't go through the wall. Do we still have a no. So the wall is here at x equals 0. Yeah, so x min might, so this maybe, well, and it should be symmetric, so I should probably move this over a little bit. Oh no. Maybe here, maybe this is x max, and then maybe here is x min. So I didn't draw the forbidden region over here because the block, it just doesn't even make sense to talk about the block being there. Right, so we have an equilibrium point at x equals x naught. Equilibrium points only exist equilibrium points do not exist for gravitational potential energy functions, or at least ones near the surface of the Earth, because it's a linear function. There is no place where the force is 0. Here, though, we know that there's a place when the force is 0. The force is 0 when the object, x min is not necessarily 0. The force is 0 when the object is at equilibrium. So What does that mean? So equilibrium points occur in general for potential energy functions. Equilibrium points occur when the slope is 0. And the way that you can see that is just, so by definition, an equilibrium point is a place where the object would be happy to sit if it's just left alone, right? Like, for example, if you just attach an object to a spring and you don't like push it or get it going, it'll just happily sit there. That is an equilibrium point. And what that means, that it'll just happily sit there, it means that there's no net force. So the way we can view equilibrium points from a potential energy perspective is, well, what would the potential energy look like where there is 0 net force? Well, we know that the slope, or the derivative of a potential energy function, is the force. It's really the negative, and so this is to say, when the force is 0, the slope of the potential energy function should be 0. In particular, anytime that you have a slope of 0 somewhere on your potential energy function, you have an equilibrium. And this is clear here. So this would be an example of a stable equilibrium because the forces in this case point towards the equilibrium. So one way to see what direction the forces point on an energy diagram is look at the slope of the potential energy function. No, it still works. It's just the potential energy 0. So the kinetic energy would just be the whole thing. If the graph was a horizontal line with no slope, where would the equilibrium? It would all be equilibrium. That just means that there's no force. The potential energy is just constant. So we can actually figure out what direction forces are just from energy diagrams, right? So we know that the force is the negative derivative of the potential energy. So in particular, if the slope is positive, like it is over here on the right, the force must point in the negative direction. If the force, on the other hand, if the force is negative, like it is on the left, the force points in the positive direction. And so what we can see here is the forces near the values, the positions of the equilibrium point back towards equilibrium because the slope is negative to the left of the equilibrium. So that implies a force in the positive direction, and the force is positive on the right side of the equilibrium, which implies that the force is in the left direction or negative. So we can actually understand even more than just, turnaround points. We can actually even talk about things like the direction and magnitude of forces. You just look at the slopes. The slopes contain all of the information about forces that you need here. So I'm going to call it there on energy diagrams. There is a relatively important example called the Leonard-Jones potential, which is outlined in grave detail in section 3.7 in the LibreText. I highly suggest you look at it. Basically, it explains how like the force between atoms. It's important, but it'll take a very long time to go through. And so I'm going to leave it up to you guys to do some reading on that on yourself. Just take a look at the LibreText. It's at the bottom of section 3.7. So I'm going to move on, and we're going to, did you say each turnaround point points? No, the turnaround points are just locations. The forces point towards the equilibrium point, and that implies that the equilibrium point is stable. If the forces pointed away from the equilibrium point, which you could imagine might look like something like this, you have slope of 0 here, and you have a negative slope there, which means a force to the left, positive slope here, which means force to the sorry, negative slope means slope to the right, positive slope means force to the left. This would be an unstable equilibrium point, because if you just nudged something here, it would just fall off. Anyway, we are going to talk more about stable and unstable equilibria later once we start talking about rotation, but we're not there yet. This just is a nice way to visualize what's happening from an energy perspective. All right, but now we're going to change gears heavily. So we're going to talk about impulse and momentum. So that's going to be the main subject for today. So thinking back to when we were first talking about work told us how the force on an object changes the motion of the object when it is applied across a distance, right? So like if you push on an object for 5 meters with some force, that will the work is the quantity that tells you how much that object's speed will change from the work energy theorem. But we could also ask how the force acting over a duration affects the motion, i.e., let's say I apply a force for 8 seconds to an object. Well, how will that affect the motion? Can I characterize that sort of, or can I use mathematics to understand that the same way we did the work energy theorem? And the answer is yes, and that's what we're going to do today. So hopefully it's sensible and intuitive to you that applying the same force to an object for a longer amount of time would change the velocity more. And the reason it does that is because it means that the acceleration of the object lasts longer. And so if the acceleration lasts longer, then the change in the speed will be greater. So just like work, because the force can change direction, we only really look at the effect of force over a short duration. So remember, back when we were first talking about work, we looked at the rate of change of speed, and we ended up with something like the d of kinetic energy equals force dotted into the small path length. We're going to do the same thing here. We are interested in a force applied over a short duration, and we want to know how it changes the motion of the object. And the reason why we care about short durations rather than like 8 seconds or like 100 seconds or whatever is because the force can change direction. So we kind of want to build it up infinitesimally, and then just like what we did for work, where we started off with the infinitesimal change and then we integrated to get the total change, we're going to do the same thing here. We just want to treat the force as constant at a given instant in time. So what we do is we define a new thing, which is just this thing called dj. It's a small amount of j, and we'll talk about what j is in a minute. And all that is it's just the force times the small amount of time over which that force is applied. That's all it is. And so we're going to investigate the properties of this thing dj and see how the existence of dj, or rather eventually it'll just be the integral of dj, which is just j, how this quantity j affects the motion of our object. And so what we're really going to be looking at is j is kind of going to play the role of work. So just like how we wrote that a small amount of work done was force.dl, here we have a small amount of this j thing is force times dt. So to find the total effect of force across a duration, all we do is integrate. And we will explain what this dj is in a minute. No, it's not. There's only, how can it be a dot product? dt isn't a vector. This is just a regular old multiplication. The total effect of force for a duration can be found by integrating. So what we have is we have the total j, and I'll give it a name in a minute, between times a and b. No longer is this, by the way, positions a and b. It is times on your stopwatch that you label ta and tb. This would just be equal to an integral from ta to tb of the force times dt. That's all. So this is actually a definition of the quantity j. This is how we define j. So if you see j anywhere, this is what they mean. And so what we call this thing, we call it impulse. J is called impulse. It is the impulse is it's kind of like, the way to visualize this is like the amount of kick that a force is. Yeah, J is not work. J or impulse is the amount of kick that a force gave to an object. Like you can measure the impulse of a collision by measuring how much it's basically like, I don't want to put it in too vague terms, but it is literally just like the kick that an object gives, or that one force gives to an object. So this quantity impulse is similar to work, but it has a few differences, and it implies that they just are separate things. They're kind of related, but they are 100% separate. So the first thing to notice is that the units of the impulse are different. the units of impulse are newtons, because force, times seconds, because dt. So this is just Newton seconds. Whereas the units of work are joules. So these are different. Joules are Newton meters, impulse is Newton seconds. Similarly, or differently, I suppose, work is a scalar. It's just a number, 5 joules, 98 joules, whatever. Impulse is a vector, right? It points in a direction. It is a vector, has a magnitude and a direction. So work is the effective force with respect to distance, while impulse is the effective force. Yeah, basically. Yeah, that's basically what it is. And then finally, whereas the amount of work done depended on the path through space that an object took to get from point A to point B, the amount of impulse that an object gets doesn't depend on a path. You can only travel in one direction through time, right? You can only travel at a rate of 1 second per second through time. So J is not a line integral. It's just a regular old integral. It has a few components because it's an integral of a vector, but it's still just a regular old integral. So what we want, so a priori, this is just like a thing, and we don't yet understand how it relates to the motion of the object. So just like work, like we don't care about the work done on an object until you know that the work is related to the kinetic energy, because then that tells you how the speed changes. We don't care about impulse. We care about how impulse affects an object's motion. So we want to relate it to the object's motion somehow. So that's what we're going to do. So to do that requires a calculation that will lead us to a thing called momentum. So we're just going to kind of back up a little bit. So the total impulse done on an object, or gained by an object, sorry, that shouldn't be a vector, from A to point B, or from time A to time B, it's the integral TA to TB. Now this is the total impulse, so this would be the net force times dt. But we know from Newton's second law that the net force is just the mass times the acceleration of the object. So this is m times the center of mass acceleration, dt, right? And mass is constant, presumably. And so when you integrate acceleration, right? If you integrate acceleration with respect to time, you get velocity. So this is just mass times the center of mass velocity evaluated from TA to TB. Put another way, this is the delta of the mass times the center of mass velocity, or giving it a new name, it's delta P cm. So that's the center of mass P. So what is this thing P? So it's just a new definition. So we define P, it's a vector, to be momentum. This is a new thing that you guys may not have seen yet before. It's just a thing. It is momentum. It's mass times the center of mass velocity, or rather, momentum is mass times velocity. So the center of mass, or the center of mass momentum, is mass times the center of mass velocity. And so in particular, for a single object, momentum is the product, let me write this, which for a single object, it's the product of the mass and velocity. Now, things get a little bit hairier when you start talking about systems that have more than one object in it. Like if you talk about the Earth and the apple that you're throwing up, not vomiting, throwing upwards, as a single system, then the momentum is a little bit trickier, because the apple is traveling at some speed and the Earth is traveling at a different speed, and they have different masses. So you'll have to combine them in some certain way to get the center of mass momentum. So what impulse tells us is it tells us how the momentum of the center of mass of a system changes. And if the system is just a single object, then it is just the momentum of that single object, which is just its mass times its velocity. So this is just to say that P is mv. Right, so the relationship that we just derived here to here gives us the impulse momentum theorem. Just like how we had the work energy theorem, we have impulse and momentum, which just relates the amount of impulse that an object gets from a force, or from the net force, to the change in the momentum of the object, i.e. the total impulse between times A and B is equal to the change in the center of mass momentum of the system. That is the impulse momentum theorem. So it's written on a separate order. For the work energy theorem, it was change in kinetic energy equals work. It doesn't matter though. But the point is impulse is like work, momentum is like energy. So impulse and work both come from external effects. Work and kinetic energy and momentum are internal properties of the system. So the question then arises, what actually is momentum, right? So momentum, like it's a word, definitely true. But I mean, perhaps more importantly, it's just another descriptor of the motion of an object. So kinetic energy is just a number, right? It's like some amount of joules. It's like 19 joules. This object has 19 joules of kinetic energy. Well, so when we say that, what that means is that is a property that the object has. And if you leave that object alone, it will continue to have that property forever. And so that property is related to things like the speed and the mass of the object. Similarly, sorry, neck had to pop. Similarly, the momentum of an object is just a property of the system. And so it's a property of the system that describes the motion. If an object has, say, 5 Newton seconds of momentum, also kilogram meters per second is the same thing, has 5 Newton seconds of momentum in the in the x direction, that just is a property of the system. It tells you something about the motion. It would let you solve for the velocity, for example, if you knew the mass. So it's just it's not something like mystical. It just describes in a new way a property of the system. Now, just as an aside, all we've done is introduce a new variable, p, where momentum cannot describe force. No, momentum is not force, vice versa. They're related by the impulse momentum theorem, but no, they're not the same thing. So all we've done is we've introduced, no, momentum is also not related to acceleration. So all we have done is introduce a new variable. P, which is equal to mv. So Newton's laws become, or Newton's second law becomes, if we do that, if we just replace v with p over m, what is the unit of momentum? It's the same as the unit for impulse. It's just Newton seconds or kilograms. I mean, it's like, let me write this here. It is kilograms times meters per second, right? It has the units of mass times velocity. And this could also be written as Newton seconds. Either one's fine. So if we do this, this just means that the net force is the time derivative of momentum, of the center of mass momentum. Because like if you just replaced PCM with MVCM, well, the ddt will pass through the m, and it will take a time derivative of velocity, which becomes the acceleration. So this is just a slicker way of writing Newton's second law. Remember, all we did to get work was we just used Newton's second law, and we did the same thing here. We just used Newton's second law to rewrite something in a way that's useful. And the reason why it's useful is because it gives us a conservation type law. If there's no external, if there's no impulse done on the object, then the then the momentum doesn't change. So just a quick useful fact that will be helpful later. Kinetic energy is 1/2 mv squared, right? But we could do some algebra to that and write this instead as m times v squared over 2m, which we could replace the mv with p squared. Remember, p squared, that really means it's the vector squared, which is just p dot p over 2m. So in fact, momentum and kinetic energy are related. The kinetic energy of an object can be found by taking the dot product of the momentum with itself and then dividing by twice the mass. Sometimes you only know things about the momentum, and maybe you don't know things about the mass, so you can't figure out the speed. So it's a useful relationship. So just as a quick again, a quick recap, because we're talking about, we're relating momentum a lot, kinetic energy and work to impulse and so on. Remember when we first, what was it? Like last Wednesday, I want to say, when we first started talking about work and breaking up the work into internal and external works, and then breaking up the internal works into conservative and non-conservative forces, sorry, into conservative and non-conservative works, we noted that the internal forces didn't just like cancel out, right? Like, for example, if you have the two blocks sliding across each other, that is a force that's internal to the system of the two books or the two blocks. But they don't just have no effect. What they do, what that sliding force does, is it decreases the kinetic energy of the system and increases the thermal energy. Similarly, for conservative forces, conservative internal forces, the kinetic energy can be changed by forces internal to the system. However, in that case, the kinetic energy is transformed into potential energy and can then be converted back later. So that is to say, work doesn't really have a third law equivalent. And I've mentioned that before, but this is kind of like, if there was a third law equivalent, like if every work was equal and opposite the work of whatever, if that were the case, then internal works would always cancel each other out, because anytime one object does work on another object, the second object also does work back on the first object. But because the works aren't necessarily the same, because there is no third law for work, they don't cancel out. So that's a recap. But the point is there isn't a third law for work, and that's why you have things like potential energy and thermal energy, because those internal forces don't cancel each other out in the form of work. The kinetic energy can change, and then we talk about how that kinetic energy changes by introducing new concepts like potential and thermal energy. So the question then is, does the same sort of reasoning hold for impulse and momentum? Is it the case that, you know, the internal forces will cause the impulse to not, or even though the internal forces are equal and opposite, maybe the impulses are not, and so the internal impulses won't cancel out, and then you might end up with like potential momentum or like thermal momentum or whatever. That's a question that would be reasonable to ask, because we saw that same sort of thing happen for work. So let me write this down for a second. Is there a third law for impulse? i.e., can we break up impulse into internal and external impulses and then categorize the internal impulses as conservative and non-conservative and so on? Does that work? So it turns out the answer is no, and I'm going to explain why. So let's suppose object 1 acts on object 2 with force, let's say F1 on 2 for a duration dt. This is just a small duration. In fact, it's infinitesimal, but it's just small. It's fine. So then, because of Newton's third law, and this is Newton's third law for forces, we can relate that force that object 1 applies to object 2 to the force that object 2 applies to object 1. We have that the force that object 2 applies on object 1 is equal to negative the force of object 1 on object 2, right? That's Newton's third law. And then because object 1 applies that force to object 2 for some duration dt, object 2 also applies its force on object 1 for that same duration. So what this implies is it implies that the impulse that object 1 applies, or rather the impulse that object 2 applies on object 1, is equal to the negative of the impulse that object 1 applies on object 2. And these are, we can think about impulses in the same way that we think about forces, i.e., or sorry, the same way that we think about work, i.e., you can think about the impulse from a particular force, and that's what we're doing here. And so then the question is if these were both internal to the system, would they affect the momentum? Would they affect could they possibly change delta P, or could they possibly change P? The answer is no, because the total impulse that is internal to the system would be the sum of those two impulses, which is just 0. So any internal impulse just cancels itself out automatically, just from Newton's third law. So this is just to say there is a third law for impulse, i.e., if one object does 5 units of impulse in the positive x direction to a second object, the second object, by Newton's third law, does 5 units of impulse to the left on the first object. And let me just write this in words. All internal impulses cancel out. So what that means is, because there is no internal impulse, there is no way that internal forces can change the momentum, i.e., we can't move them. There's nothing to move over to this side to then group into like change in potential momentum or something like that. There's like anything that we would want to move over, any internal forces just contribute nothing to the overall impulse. So this is all to say, well, I just said it, so I won't write it, but there is no momentum version of potential energy and thermal energy. All there is there are external impulses, and there is the momentum of the system. There's no potential momentum, there's no thermal momentum, whatever. It's just external impulses and the change in momentum. That's it. Internal force. So this is really, really good, because if you choose your system properly, it makes the problem really, really simple, because you don't have to worry about internal forces. All you have to worry about is external forces, and then you can say something about how the speed or how the velocity changes, which is really strong. And so in particular, if there are no external impulses, and remember, impulse is just an integral of force. So if there are no external forces, then there's no external impulses. Then the change in the momentum is 0, which is just to say again that the momentum would be conserved. So if there are no external forces to your system, the momentum of your system, from all we've just done, never changes. And we've already seen how conservation laws can be really powerful. They let you solve hard problems. Things like how high would a ball go if you shot it up at some speed? Energy conservation gets you that answer. Now, with another conservation law, we can solve even harder problems. And we will talk about those harder problems probably next week after the midterm. These are things like you shoot a billiard ball at another billiard ball. What happens? What direction do they bounce off in, and so on? All of those things are things that you need momentum conservation for. Just as an important note, remember that momentum is a vector. Kinetic energy is just a scalar, it's just a number, but momentum is a vector. And so really, when we write delta P equals 0, that's really like 3 equations, right? Assuming you're working in 3 dimensions. That means that the x component of the momentum is 0, it means that the y component of the momentum is 0, and it means that the z component of the momentum is 0. Precisely, Gabriel. So this is actually 3 equations in 1, which makes it even more powerful than energy conservation. You can get more out of it. Now, there's one extra thing to talk about, which is this notion of partial momentum conservation, which is really handy. So when we write, like I just said, when we write that the external total impulse is equal to the change in center of mass momentum, we really mean that, so let me write this out. So this, which I just described, really means the following. It means that the x component of the external impulse is equal to the change in the x component of the momentum. The y component of the external impulse, equals the change in the y component of the momentum. And the x component, the z component of the external impulse is equal to the change in the z component of the momentum, right? So this is actually 3 equations, which is super handy. And so if, for example, if we knew that this one was 0 and the others we didn't know that they were 0, maybe like a good example might be a projectile motion, right? Let's say you shoot a cannonball. Assuming there's no friction, there's there's no external forces in the x direction, in the horizontal direction, right? So in that case, this equation would give us 0 equals delta p cm x, even though there might be impulses in the other directions. So you can actually apply momentum conservation rules or momentum conservation ideas, even if the total momentum vector isn't actually conserved. It will let you, you can still partially use momentum conservation just because there's 3 equations, and if one of those equations you can figure something out from, then that's good. That's all you need. I'm actually going to erase that because that shouldn't go in my notes. That's not generally true. But the point is you can, if you know that at least one of these is useful, say you know the impulse in one direction but not the others, then you can still use that equation even if you don't know the other ones. So this is all just to say you can get a lot out of the impulse momentum equation. Right. So we're actually making pretty good time. We have to talk about center of mass, which is a bummer because that's going to take a while, but may as well get started. So we're going to take a detour for a while away from momentum conservation, and we will go back to momentum conservation next week, and maybe a little bit at the end of Wednesday. But we have to talk about this notion of center of mass. So we've been definitely putting it off. Like, it showed up in Newton's second law in like the second week of class, and it's showing up a lot here. So we should probably lay it down once and for all what center of mass really is and how one uses it in calculations. So as I've already mentioned, momentum is super useful when there are only internal forces, right? Because in that case, then there's no external impulse. And so then it's really easy to use momentum conservation to solve problems. You write, initial or final momentum minus initial momentum equals 0. If you know the initial momentum, then you can find the final momentum and so on, right? And so the way that we typically set up our systems to do that is we just make our system bigger and bigger until there are no external forces. So imagine, for example, I throw up an apple, right? If the apple alone is my system, then there are external forces, and hence there would be external impulses because there's gravity acting on it, which is an external force if the Earth isn't part of the system. So what we do instead is we just make our system bigger. It's the apple and the Earth. And now we ask, okay, well, now there's no external impulses, so now we can just solve the problem. So so we can do that just fine, but now the position of the system maybe makes less sense. Maybe the mass of the system makes less sense, things like that. So we have to be careful. And to do that, to handle those sorts of things, to handle large systems with lots of chunks of stuff in them, we need to untangle this notion of center of mass, which is often abbreviated CM, or sometimes you'll see me abbreviate it COM. So first things first is the mass of a large system or mass of a complicated system is pretty easy. So if you see an M up here, but you're talking about a system with a whole bunch of different objects, it's just the total mass of the system. So that one's easy. So if you saw an M appear in your equation when you were talking about the system of the Earth and the apple, well, that total M would be the mass of the Earth plus the mass of the apple. So that's what you would use in those cases. So in F equals MA, where F is F net and M is the mass of your system and A is the center of mass acceleration, well, the M in that case is the mass of the whole system. However, it's a little bit harder when we start talking about position and acceleration and velocity as center of mass quantities if you have a complicated system. And maybe momentum. What are those quantities? It's a little bit, so when I say complicated system, I just mean a system that's not just a single thing, right? Maybe the system is my pen and my phone, in which case the mass would be the total mass of the pen plus the total mass of the phone, right? Yeah, so when I say complicated system, I just mean a system that's not just a thing. It's more things. I didn't want to say large system because that could imply something about size. So these all depend, they all depend on a place and the movement of that place. Right, so like the vector r typically indicates the position vector for an object. If you just have a single object, it tells you about where that object is in space. And v and a, they tell you about how that place moves through space, right? But if your system is more than one object, if it's a phone and a pen, well, what place does r refer to? What motion does v and a refer to? Those are the questions that we have to answer. So let's start by, oh, it's 2 o'clock. So actually, we won't do that. We won't answer that. We'll leave that till Wednesday.